To maintain the momentum of national railway networks, operators must manage an incredibly complex, constantly shifting physical infrastructure. Historically, ensuring a train is actually safe for passenger service comes down to brake power certificates, or BPCs. But tracking these certificates, along with routine maintenance schedules, often relies on siloed, paper-based workflows. These manual logbooks create a severe operational bottleneck. Data gets trapped on physical clipboards, leading to delayed supervisory approvals, opaque audit trails, and a maintenance culture that can only react after a component has already failed. To establish a digital baseline, Indian Railways deployed RailCare version 1.0, an application initially targeting the maintenance of high-performance Vande Bharat train sets. RailCare serves as the mandatory data foundation for a unified predictive maintenance ecosystem, moving far past the scope of simple paper replacement. You cannot deploy true AI-driven predictive maintenance overnight. It requires a rigorous, sequential architectural build to ensure the underlying data is actually reliable. Phase 1 focuses on removing friction at the ground level. This means engineering highly responsive mobile interfaces and critical offline capabilities to guarantee flawless data capture from the depot floor. Phase 2 takes that pristine mobile data and automates the workflow, connecting field inputs directly to wider enterprise APIs and inventory management systems. Only in Phase 3 can you layer IoT sensor data and machine learning algorithms on top of that established pipeline to achieve condition-based monitoring. Skipping straight to Phase 3 results in algorithmic failure. Any advanced analytical model is only as powerful as the friction-free field data feeding it. Version 1.0 establishes this baseline by successfully digitizing centralized inspection records, overdue maintenance alerts, and precise coach composition. Looking at this live rake tracking module, we see the exact operational data supervisors monitor: incoming train numbers, coach counts, and maintenance types. The critical metrics here are BPC granted status and validity date, which determine immediate operational readiness. However, despite this back-end capability, a gap analysis reveals a systemic risk. If field staff face a high cognitive load while using the app or struggle with poor network connectivity, the data pipeline breaks down. In an industrial setting, a clumsy user interface encourages workarounds. If it is faster to write something on a notepad than log it in the system, enterprise data integrity actively degrades. To solve this, Phase 1 introduces specific UI enhancements. This layout outlines a modern dashboard with role-based KPIs to streamline navigation. Features like Material Design 3, Universal Search, and Dark Mode ensure the application remains readable during low-light night shifts. Manual search is bypassed using QR code integration, instantly retrieving engineering details and maintenance history. Next, the digital checklist enforces mandatory upload of photos, videos, and voice notes. Finally, the offline mode caches all inspection data locally, automatically synchronizing the moment connectivity is restored. These UX improvements and offline failsafes are not optional luxury features. They act as absolute prerequisites for capturing perfect, uninterrupted maintenance data. Once that field data is perfectly captured, its value remains limited if it stays isolated. To generate systemic operational intelligence, it must immediately integrate with the broader railway enterprise architecture. This integration map illustrates how the central RailCare node connects the localized mobile app to various enterprise modules. By linking to real-time inventory systems, supervisors optimize parts planning based on defect reports. Furthermore, secure digital signatures establish a tamper-proof, audit-ready compliance trail. Through these Phase 2 API connections, localized depot actions are transformed into unified, nationwide operational intelligence. With frictionless data capture and a fully integrated enterprise ecosystem established, the architecture is finally ready for Phase 3, advanced predictive analytics. Feeding live IoT sensor data directly into the RailCare platform allows operators to abandon rigid, reactive maintenance schedules in favor of dynamic, condition-based alerts. This chart visualizes the twofold target outcome. Over time, the data pipeline allows railways to maximize the mean time between failures, while simultaneously driving down the mean time to repair. By continuously analyzing component failure trends, artificial intelligence algorithms can recommend highly specific maintenance priorities, targeting high-risk components long before an unexpected breakdown disrupts passenger service. Consistent AI-driven train availability is the cumulative result of executing a rigorous phase-by-phase data architecture. Because the underlying digital workflows and checklists are standardized, this architecture is inherently scalable. This diagram shows how a single unified platform hub can distribute these digital processes outward across entirely different asset classes. The immediate roadmap expands the initial deployment on high-performance Van de Barret train sets to include conventional LHB and ICF passenger coaches. Over the long term, this expansion incorporates heavy industrial rolling stock, bringing freight wagons and locomotives into the exact same digital ecosystem. A single, horizontally scalable platform consolidates isolated maintenance workflows, providing administrators with complete network-wide visibility over thousands of diverse assets. This evolution requires a calculated sequence, starting with an offline-capable mobile interface, expanding outward through enterprise API integration, and culminating in IoT-driven predictive analytics. Executing this roadmap delivers absolute safety compliance, highly optimized resource utilization, and peak asset reliability across the network. Ultimately, RailCare represents the definitive blueprint for modernizing legacy transport infrastructure into a fully integrated, data-driven digital twin.